Okay, let's revise. So, conditional probability and independent events is what we're focusing on. This is area study 4, which is falling under probability. If you didn't know, there's 4 areas of study, and 3 of which you've learnt all of it already. It's now area study 4, it's just probability, and we're looking at dot point 2 under discrete probability hyphen number 5. Yeah? Very simple ideas, just talking about including conditional probability. You need to be able to use or understand how it applies into discrete probability. Now I'll talk more about discrete in the next session and then introduce the mean, variance, and standard deviation. But at this point, we're just revising year 10 and 11 mathematics. Okay, conditional probability. Now, for those who found it hard last year for conditional probability, I'm going to try to explain it again as a second time and then how that relates to independent events. Conditional probability is the probability of an event A occurring when it is known that some event B has occurred. Now I know when I write that, you either get it or you don't get it. The way I sort of try to explain it is when I say the probability of an event A, remember event is something happening. It's like a set, it's a group of things. So if I said something has happened, and the example I had to give last year, I said if there was a stick and Mr. Tran was walking on his pathway always from A to B, every time he walks, if let's say he tripped the first time on the first day, the likely chance of him tripping again on the second day, so if A had occurred, meaning he tripped once, day 1, the chances of him tripping on day 2, is that more likely, less likely, or equal if he tripped yesterday? Logically, I'm asking. Probably less likely. Now, the reason why you say less likely is because yesterday he tripped over it. So therefore, he would remember, like, oh, that's right. Yesterday there was a stick here. Let's pay attention. So it's less likely. But if I said that on day 1 I tripped, and then day 2, me being oblivious again, day 2 I tripped, and then day 3 I still tripped, this is called independent. Because regardless of how many times I tripped the day before, it doesn't matter. I'm always going to trip because that's just my chances of me tripping. It's independent of that. It's always going to happen. So when I say probability of an event A occurring when it is known that some event B has occurred, okay, so if you want to find the probability of me tripping, given that yesterday I had already tripped, if yesterday's event had occurred, it affects my next one. That's why we say it's conditional. It's conditional on the sense that it's dependent on what happened before. Independent events does not depend on anything that happened before. It doesn't matter if I tripped the day before, I will still have the same chance of tripping over it. Whereas if it does depend on what happens before, then the fact that I tripped today will affect tomorrow and the day after. Okay, so the probability will change. Okay, that's what conditional probability is, and the difference in the mindset is there. Okay. Now, that then leads you to this rule, which last year I give you the logic to it as well. Actually, hold on a second. I'm just going to take off the... This is how it's written. When you write probability, which is PR, bracket A with the vertical line, that means given. Okay, so probability of A given B just means what's the chances of A happening if you knew that B had occurred? If I had to translate that, boys, thank you. Once more, I'll kick you guys out. You guys can stay out there. Fair call? Probability of A given B just means if you had to translate it to the example I just gave, it's the chances of, what's the chance of Mr. Tran tripping over the stick, given that yesterday he had tripped it already. Okay, that's what it's really saying. So the probability of A occurring if B had occurred already. Okay? That's given by this rule. So the chances of that happening is, well, what's the chances of Mr. Tran tripping on the first day and the second day? That's what the intersection means. What's the chances of both of them happening at the same time out of the probability of him tripping yesterday? Okay. Now, I think the most difficult part is right here. Why is it out of? what happened yesterday. Why is this rule true? Now in the next slide I'll try to explain that. Why the sample size has changed. Okay, because we're saying that given this had already occurred, we're looking within this bracket. If it had already occurred, what's the chances of it happening again? That's what we're looking for. Okay, that's why it's the sample space. Remember, probability is number of favorable outcomes out of your total outcomes. But your outcomes have changed now. If you knew there was a sample size that you're looking at, you're saying this had already occurred. Now, what's the chances of it occurring within that? That's what you're looking for. That's why this formula is true. Okay? Let's do an example just so you can see why it works. Now, if you rearrange this, this is your tree branch. And I'm going to talk about that when we draw a tree diagram. You're actually doing conditional probability when you draw the tree diagram. Okay? And that's all this is saying. Probability of A and B happening is the chances of what happened first and the chances of happening again. So if you have to translate this into what my example was before, this is just saying chances of Mr. Tran tripping on the first time times by the chances of him tripping the second time tells you the probability of him tripping twice. So if this was Monday and Tuesday, chances of Mr. Tran tripping on Monday, chances of Mr. Tran tripping on Tuesday if he had already tripped on Monday. This is the probability of him tripping on both days, Monday and Tuesday. See, that's what this symbol means. It means and. So it happened on Monday and it happened on Tuesday. Okay, this is just Monday only. This is Tuesday if we knew he tripped on Monday. Okay, I'm going to draw a tree diagram later so you can see what that means. But that's your multiplication rule from your conditional probability rule. Okay, now let's think about the logic of this formula. I tried to illustrate in this, taking this diagram from a picture. Let's say this is like rolling a dice. So you got your 1, 2, 3, 4, 5, 6. Yeah? Chances of getting B is 2, 4, and 6. Chances of getting A is 6. Was the number 6. So let A is getting 6, let B getting even numbers. If I said, what is the probability of rolling a 6, meaning getting a 6, if you knew or given that you already have an even number? You see, this changes the problem because if I said, what's the chance of you getting a 6? You would tell me it's 1 out of 6, rolling a dice. This is your favorable outcome out of your total outcome, which makes sense. You only got the one number, 1 6 out of your total outcomes, which is 6, which is why you say it's 1 6. But when I ask you, when I say, what's the chance of getting a 6? So probability of getting a 6, given that you already know you've got an even number. You already got that already. So regardless, you already know you've got an even number. Now what's the chance of you getting 6? Well, logically, an even number, if you knew you got an even number, you either have a 2, 4, or 6. So your sample space now becomes 3 options. You either have a 2, 4, or 6. And I'm asking you, what's the chances of you getting a 6? Well, out of those 3 numbers, there's only one of them. That's why your sample space changes to 1 out of 3. Now this is exactly the same as saying, what's the chances of you getting a 6 and it being an even number? Divided by the probability of getting an even number. See, that's why this rule is linked to the slide before. We said the probability of A intersection B divided by the probability of your sort of what you're looking for, what has already happened. In our case, what has already happened was that we're looking for an even number. We already know it had occurred. We know that we have a 2, 4, or 6. What I don't know is, what's the chance of getting a 6 if I already knew I have 2, 4, or 6? What's 1 out of 3? Out of 2, 4, or 6, the chance of me getting a 6 is 1 out of the 3 outcomes, not 1 out of 6. So the probability for this one is chances of getting a 6 given that you already had an even number. Okay, that's the difference. And the key part is understanding that part there when you say given. Okay, that's a really big part to understand when it says given. Now, I'm just gonna try to show you. You can also use, I'm just gonna somehow delete all this. You can use a Carnot map to see this issue as well. Notice n, just in case you forgot the notations again, n means the number of elements. So number of elements for B, number of elements for not B, elements for A and not A. Yeah? In total, you got 6 elements. You got 1, 2, 3, 4, 5, 6. So in total, that's why I wrote number 6 there. We fill out the data. Number of A, well, I only got 1. I got the number 6 out of my 6. So that's why I only got 1 of them. In terms of how many numbers that are even, well, I've got 2, 4, and 6. That's why I wrote 3. There are 3 elements there. If I have to fill out the bottom table, and I can see that what's the intersection between A being a 6 and it being an even number, well, this is the intersection. There's only one that's an intersection that they both have in common. So if you had to write out B, that was 2, 4, and 6. That's a 6. What's common between the two? 6. That's why I have 1 element, which is why I wrote 1 here. Okay? So, now that I've got 1, I can fill out the table and say that means this has to be 0, because 1 plus 0 will give you 1. 1 plus 5 will give you 6. 3 plus 3 will give you 6. And you can work this out. This is 2. And therefore, this has to be 3. Okay, so I'm just filling out the table. Now, if I'm answering the question, once you fill out the Carnot maps, you can actually say, now, what's the chances of you getting a 6, given that's an even number already? Now, this is the even column. If you already know you got an even number, so out of the 3, what's the chances of you getting a 6? Well, this is not 6. This is chances of you getting a 6. So it's the 1 out of 3, which makes sense. Okay, if you had to write it all out, that's just the probability of A intersection B over the probability of B, and that's what I just did. 3 represents the B, 1 represents A intersection B. And that's the rule for conditional, logically. Okay. And if that still doesn't make sense, then I think the other example that I had would also explain it as well. But you can have a look at that slide if you like. Again, if that doesn't make sense, I really need you to gel that understanding, because without that, that independent events doesn't make sense to you either. Okay? Now, the example 1, I just want to get you to look at this and read this question. You don't need to do too much mathematics here. You can actually, if you understand what I was just saying about conditional, you can look at this question and tell me what the answer is. Okay? So it tells you here there's 1,000 drivers. So you got a total 1,000 elements. It says that it's classified into age and number of accidents. So you got age, you're either less than 30 or older than 30. You either got 1 accident or more. Actually, it's you either have 1 accident or you have more than 1 accident. Okay? Now the question, let's have a look at the question. We've got our data there. The question says, if you're selecting at random, given that the selected driver is less than 30 years of age, okay, so given that you already knew, this person is less than 30 years of age, so they're less than 30, what is the probability that the person has more than 1 accident? So if I had to write this out as a notation, I'm just asking, what's the chances of you choosing someone who has more than 1 accident, given that you already know they're less than 30. So if I had to do this mathematically or just looking at the table, I'm just looking, well, how many people are less than 30 already? Well, I'm looking at this, out of 1,000, less than 30, I already know 600. 600 people already knew, given that this person is already less than 30. So I know 600 people out of the sample, what's the chance of how many people had more than 1 accident? Well, more than 1 accident says, these are the accidents age, where you're less than 30, 470 of them has had more than 1 accident. So it's 470 out of 600 people, not 1,000, because 1,000 includes people older than 30. I just want to know people less than 30, how many are there? There's 600, so I already know the answer is 47 out of 60, and you can reduce that. But there we go. So if I just had to answer the question, this is all I'm saying. More than 1 accident, and it's less than 30, You can do all the mathematics if you want, but you didn't have to. The logic speaks for itself. 47 on 60. You didn't have to do all that mathematics to get it. You can just look at the table and say, out of 600, how many people had more than one accident? 470 of them. So 470, 600, 47 out of 60. Do we feel a bit more comfortable with the idea? Yes? No? Yeah? Okay. Because if you understand that concept, that's from year 10 and 11, it leads to the next one. Independent events, which I tried to describe before, I said that it doesn't matter what happened before, your chances of tripping, or Mr. Tran tripping over the stick, is consistent. He will always trip over the stick. It doesn't matter what happened before. So how's that change things? That only changes one thing. If this is the conditional probability rule, we said that the chances of getting A depends on whatever B was. But if in independent events we're saying that it doesn't matter whether B occurred, then what I'm saying is this now is the same thing as saying that the chance of you getting A given B is actually just the same as the chance of you getting A. It doesn't matter what B is. Who cares about B? The dependence does not matter. So that means the chances of you finding A has always been the same. It's like a good example is flipping a coin. If you flip a coin, chances of you getting tails, still half. You flip it again, still half. You flip it again, still half. Doesn't matter if you got tails, tails, tails beforehand, the chances of every time you flip a coin, it is still half. Doesn't matter what happened before. And that's exactly the same here. Mr. Tran tripping over a stick day 1, day 2, day 3 does not matter if he knew he had tripped over the day before. That's when independent events occur. Okay? Why does that change things? How does that change things? That means that the formula now that changes your probability in the sense that A given B no longer is a problem. It's just finding out probability of A. So therefore, if you rearrange this now, you get PR of A times PR of B equals to PR of A intersection B. And that was one of the rules that you had to learn last year, and it's the only one rule that if they asked you for independent events, that's all you had to prove. You just needed to prove that if A times event B, if it equals to the intersection, they're independent. Okay? And that's typical of flipping a coin. So like heads, tails, heads, tails, heads, tails. If I asked you, this is half, 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 and half. And if I asked you, what's the chances of you getting tails and tails? Now you can look at the sample space. You can look at the sample space and you say you got a HH, HT, TH, or TT. So if I ask you, what's the chance of getting tails and tails, you will look at that and say, well, it's 1 out of the 4. Or you can actually use this rule of multiplying the branches, multiplying T and then T again, that's half times a half, is also a quarter. So therefore, flipping a coin is independent. They're independent events because I multiplied PR of A times PR of B equals half. I looked at the sample space and found out, is the intersection, like what's the chances of getting T and T? It was also a quarter. Because these two are the same, therefore they must be independent events. Okay? And that is important. It's a very small concept, but you have to understand conditional. Because if you understood conditional, independent makes sense. You don't have to memorize that rule. Makes sense. You don't even have to memorize this rule, because that makes sense in the question. You're talking about if the sample space been reduced, you're looking specifically at a sample space, and then out of that, what's the chance of getting what you want? That's why this rule makes sense. Okay, so you can see conditional probability leads you to independent events, and conditional probability also leads you to tree diagrams. So tree diagrams, for example, the one I just did, heads and tails, heads and tails. This is how we would have done it in 10 and 11. But what you need to realize as well is that this is actually saying probability of H occurring is half. And then this is not just probability of H. This is actually saying probability of H if I knew I had H on the first go. See, if this was my first go, chance of getting H, half. Second go, chance of you getting a H on the second go, given that you knew H had occurred. So in this case, if you had to find out the chances of getting H and H, you would tell me it is PR of H multiplied to probability of getting H given that H occurred before. And that right there is exactly your conditional probability rule where you rearrange it and it's the multiplication. So if I just multiply this over here, you get probability of B multiplied to probability of A given B equals PR of A intersection B. Which is why that's what you've been doing. You've been multiplying the branches to find out your probability. It's the same thing. Okay, so that's what I'm saying. It all led from one to the other. It all makes sense along the way. Okay? Now, if you understand those two, great. That's all you needed to know. So, let's practice your questions now. Okay, so we've got conditional probability. We understand what independent events are, yeah? Now, this question is from your textbook. You can try out 9 and 10 if you want, but I want to move on to the VCAA question so you can see a simple concept is worth, I think it was 6 marks at the end of 2014, question 9. And I want to show you how it works. Now, you can look at this and how I work through it using corner maps or tree diagrams, but I want you to look at this question. VCAA 2014, 2 years ago, not long ago. You didn't need to use anything fancy. Read the question, 6 marks, pretty easy. You've got a problem. You can either draw a tree diagram or use Carnot maps or Venn diagram, I don't care. Those are just tools for you to visualize the problem. I don't need to use any of that. I just look at that and I know the answer. Now for you, if it helps, you can draw it out in any way you want. Doesn't matter how, but as long as you answer this question appropriately. It's just using basic year 10 and 11 mathematics. You're not even using discrete probability here. You're just using year 10 and 11 mathematics to answer the question. So read the question. Sally aims to walk her dog, Mac. So you either walk the dog. If the weather's pleasant, then she walks the dog 75% chance of the time, so 3/4 of the time. If the weather is unpleasant, the chances of her walking the dog is 1/3. The key step that I think a lot of students find confusing is this next line. It says, assume that pleasant weather on any morning is independent of pleasant weather on any other morning. Now I can imagine students sitting there at the end of the year in 2014 going, what is that line saying? And all it's saying, if you understood what I just said before about independent events, all it's saying is, if you think about the example I said about Mr. Tran tripping over the stick, it means that day 1 he trips, day 2 he trips, day 3 he trips, it doesn't matter. It doesn't matter, it doesn't affect the next day. So what is this one saying? It's just saying, pleasant weather on one morning doesn't affect the next day. Doesn't matter. So the next day still, the chances of it being pleasant is still pleasant, or unpleasant, doesn't matter. It could be 0.5, so it's always going to be half, 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 half. It doesn't depend on the day before. That's all it's saying. And that one line is just saying that chances of it being pleasant today will not affect tomorrow's event. That's it. That's all they're saying. So if you know that, first question, 2 marks. In a particular week, the weather was pleasant on Monday. So you know it was pleasant on a Monday, and you know it was unpleasant on a Tuesday. Find the probability that she walked Mac on at least one of these 2 mornings. Figure that out. Read the question, write out your notation. What do you need? What are you trying to find? Work that out for me. Okay, so what's the probability? Chances of what? What are you trying to find? Chances of what happening? Chances of being pleasant? Chances of her walking? What is it? What is it asking? Think about that. Draw the diagram if you have to. If it helps you, you know Monday is pleasant, Tuesday is unpleasant. How does that make a difference? Draw. Visualize. Visualize. Draw a tree diagram for me. Use a tree diagram. If it's pleasant, we don't know what the chance of pleasant being, but we just know if it's pleasant, what's the chance of you walking Matt? Looking at the question, what does it say? What's the chance of you walking Matt if the day is pleasant? 3/4. What's the chance of you not walking Matt if it's a pleasant day? 1/4. So you should have a branch that says pleasant, 3/4, 1/4. Then what if it's unpleasant then? What's the chance of you walking Matt? 1/3. So what's the chance of you not walking Matt on an unpleasant day? 1/3. So now you've got a tree diagram. You've got pleasant, unpleasant. Walk Matt. What was it again? 3/4, 1/4. On an unpleasant day, walking Matt. 1/3, not walking Matt. 2/3. Yeah? That's the first paragraph of the line. Now the second question tells you if it's independent, it means Monday, Tuesday is totally separate. Let's think about Monday. Now was Monday a pleasant day or an unpleasant day? Pleasant. So what's the chance of her walking Mac on a Monday? 3/4. So you would say, alright, so your branch, pleasant, 3/4. That's a Monday, if she does walk it. Okay? And then on Tuesday, is it unpleasant or is it pleasant? Unpleasant. So unpleasant, which means unpleasant and chance of you walking Mac? 1/3. So now it's asking you, what's the chance of you walking Mac at least once? Now think about it, Monday, Tuesday. You can either walk Mac on Monday, that's once, or you can walk Mac again on a Tuesday, that's twice. So that's more than once. What else? What else can you do that you could be walking Mac? What else could possibly happen? You don't walk Mac on a Monday, but you could walk Mac on Tuesday. That's still at least once. Or yeah, and that's so. Then, if you've got your tree diagram, you can work out the probability of that happening. You're asking what's the chances of Monday not walking and Tuesday walking. Chances of Monday walking and Tuesday walking, and chances of Monday walking and Tuesday not walking. And that's one probability there. That's the chances of at least once or more. Yes, there is. The independent events was A as a branch and then B as a branch. That's the only part that is. Alright, let's go through the answer for the first one. Let's have a look. Now, if you had to draw the tree diagram, this is the answer. Now, you have to think about it logically. if I said you always got to visualize it. If you can, it makes it easier. So, you either know it was a pleasant or unpleasant. I'm going to do P dash for unpleasant. Right? They said that if it's pleasant, you would walk Mac. I'm going to do W for walking and W dash for not walking Mac. 3/4 if it's pleasant, that means it's a quarter that's not present. Whereas if it's unpleasant, you had the chance of you walking was 1/3, therefore 2/3 is not pleasant. I mean, not walking on an unpleasant day. Okay? So, the fact that they said Monday and Tuesday are independent events, you look at them individually. You look at them individually, you either have Monday, pleasant, not pleasant, walk, not walk, walk, not walk. That's on a Monday. Tuesday, yeah, again, because it's independent, you have the same branch again. You've got pleasant, unpleasant, walk, not walk, walk, not walk. But the thing is, they already told you, Monday, they told you it's pleasant. So that means it's 100% chance it's pleasant, and this is 0. So you no longer need this branch. This whole branch here is gone because 0 times anything is going to be 0. So you're focusing on what's the chances of Mac walking on a Monday? Well, it's 3/4 and it's 1/4 not. Same thing with Tuesday. They already told you it's unpleasant. So I know it's 100% chance that you are going to be unpleasant. It's an unpleasant day and that's 0%. So that means you don't need this branch. Chances of walking is 1/3 and 2/3 not walking. Now the question was asking, what's the chance of you walking Mac at least once? Now out of those 2 days, you got Monday or Tuesday. Now you can walk on a Monday and not walk on a Tuesday. That's once or more. You can walk on a Monday and you can walk on a Tuesday. That's 2 days. That's more than once. Or you can not walk on a Monday but walk on a Tuesday, which is what I'm doing here. Now to find the probability, because it said at least one or more, once or more, to find the probability, you're just multiplying the branches. It's either 1 times 3/4 for chances of Monday walking. And if you don't want Monday or Tuesday to walk, then it's 1 times 2/3. And you add those, you times those two together, add those two together, and you get your probability for each one. Alternatively, what I did, which I thought was easier, was instead of finding the probability of Monday and Tuesday walking, and then chances of Monday not walking but walking Tuesday, and then chances of walking on Monday but not Tuesday, that takes too long. So why don't you just find out what's the chance of you not walking at all, and then subtract that from 1, because 1 is 100%. So if you knew that this is walking, walking, walking dash, walk, and walk dash, this here is the chances of more than 1. The only outcome that you don't have is not walking. So if you just found out 1 minus the probability of not walking, well then you get the probability of you walking more than once, and that's quicker. Not walking on a Monday, which we knew was 1/4, and then not walking on a Tuesday was 2/3, which is what I did here. 1/4 times 2/3, 1 minus that gives you 5 out of 6. Okay, so the first question, about 50% of them got it right, and about 50 of them got it wrong. I thought that was very interesting. From what I'm reading, a lot of people used matrices at the time, but you didn't need matrices to do that. Just use a tree diagram, it's easy to see. Okay, now, let's go back to the second question now. Now that you've got an idea how to do the first one, I want you to use your understanding to do the, whoops, how do I go back? Whoop. Oh no. I want to go back to the question. I want you to do B. Now B-double-I is considerably done very badly. It was about 27% of them getting it correct, but it's a very simple concept. You understand the stuff I said in the first 2 slides, you're set. Number I think about 40% of them got it correct. So it dropped, so it went from 50 to 40 to 30, and I think it's a very easy question. 6 marks, question 9, using year 10 and 11 mathematics. It's not hard, okay? So let's have a look. I want you to have a look at this question. Think about it. So now they tell you in the month of April, the probability of pleasant weather in the morning was 5 out of 8. How does that change things? How does that change things? So now you've got a chance of it being pleasant. Remember when we drew the tree diagram, we had pleasant, unpleasant. In the first example, you knew Monday was 100%. Now, they're telling you that pleasant is 5 out of 8. Unpleasant would be 3 out of 8. And the rest still follows the same. It says if it's pleasant, then you've got chance of walking Mac is 3/4. Chance of you walking Mac when it's unpleasant is 1/3. Draw your tree diagram if it helps. Answer the question, find the probability that on a particular morning in April, Sally walked Mac. You just want to know, what's the chances of walking? That's all you're asking. Chances of walking. That's all it's asking. Okay, given that you knew that probability of it being pleasant was 5 out of 8. That helps. Draw the tree diagram. It's actually almost time's up, but the solutions are on this PowerPoint. I'm just going to quickly show it to you in case you didn't see. Question B, if you drew the tree diagram, like I said, just draw it first. 5 on 8, 3 on 8, everything else is the same. You're just asking chances of walking. The chance of walking is just, that's walking, this is walking. Add those two together. So it's just 5 on 8 times 3/4 plus 3 on 8 times 1/3 will give you chances of walking in that month. Because it's the tree diagram. It's independent every time. So that's the chances of walking and chances of not walking. You can find that out as well. Okay? And then have a go with the second one, and I want you to look at the answers, okay? Because that was done poorly as well. So this is 44%, the next one's about 30%. So see if you can do the next one, conditional probability. Okay? All right, we'll call it a day, and I'll see you tomorrow. Sorry? Oh, sack sheets, thank you. Oh yeah, come grab one. Oh yeah, I can't remember. Okay, no. It does.
Yeah, that's what What did we do yesterday?
I'll just do that.
that you get out. I'm free at lunch, session 5 and 6. Or maybe upstairs. He's calling you big. He's calling you a tank. Well, if you were listening to what I was saying at the start of the session, clearly I know.
I got work. I'll see you next period.
Hello.
Why did you leave? There's like so many empty spots now, vacant spots.
So now you can work more.
Yeah.
Thank you.
Worth more?
Yeah, she left, so we have extra.
Yay.
I quickly check if my stuff.
Yeah. And yeah, I'm gonna leave these here in case you want to grab them.
You don't have to. I don't want. Sorry? To my neck? Yes, it still hurts.
Where did you hurt yourself? Probably Emmanuel. He would not.
Yeah, I know, I'm like Anthony.
This Anthony got us blocked. Do you remember Papa Day back then?
No, I wouldn't recommend it though.
Hello, darkness.
Okay.
Emmanuel, my friend.
Friend? Yeah.